Okay. Can you see my screen? Okay, great. Great. All right. So we continue. So we continue from where we stopped. Um, continue from we did M4 last Saturday. Okay, someone Kelly, you've got something to say. Kelly, you raised your hand.
Oh, sorry, sir. That was a mistake.
Okay. Okay. No worries. No worries. All right. So we continue with M5. All right. And thanks to everyone that attended the information session yesterday. Kick off tutorials this morning with M5 control equals to error correction over time. And we'll look at what error is. Error, it's an information, and why correction is gradual. And then we'll look at overshoots, oscillation, which is energy imbalance, stability, and then we'll look at the context, real world context. All right. And then the key terms. And then we'll do a walkthrough. We'll run the aggressive presets. I mean, the conservative and the, and then, so this is the aggressive, this is the balanced, and this is the conservative. I will explain the context of all of this as we progress. And then we'll take the quiz, then we'll move to summary. Right. And I'm sure, I hope we still have time. We'll progress with other modules. So, so before you tune a PID controller, you need to understand the fundamental mechanisms it exploits. Control systems don't fight disturbances directly. They respond to the consequences of disturbances, measured as error. And this lesson builds the mental model you need for every module that follows. So again, what we're trying to do is we're building a very solid foundation upon which you'll be able to build intuitions and understanding of other concepts. Right? These are the thinking that goes on, or these are the thinking that we programmed actually into the controllers. That's what we are trying to get. All the ladder logic, the function block, and all of those things. This is what you are trying to get them to do. This is what you are trying to automate, actually. Because disturbances are regular features. In fact, disturbances are, how can I say that now? Are regular features of life, so to speak. I mean, things are not going to be stable forever. So we have established that error is SP minus PV. And in the simplest form, all we are trying to achieve in the plant is to minimize error as much as possible. The closer error is to zero, the closer our process is to stability. Right. So that's all we are trying to do. All the PLC we are running, all the programs we are writing and running on the PLC, it is simply designed to reduce error. All the instruments we install, all the valves and everything we install, they are all designed at the end of the day, at the fundamental level, to reduce error, because we want to keep our process in a steady state, right? So without error, no action occurs. A system perfectly at set points produces, excuse me, zero error, and the controller quietly holds its current output. The moment a disturbance moves PV away from SP, error appears, and then correction begins. So the insight here is that controllers don't see disturbances. They only see error, which is the result of disturbances reaching the process variable. I hope you still remember the difference between SP, PV, MV, right?
Yes, sir.
Okay, great. Because we're using them now without defining it. So why correction is gradual? You cannot instantly eat a tank of water. You cannot instantly accelerate a motor shaft. Physical system resist change. And that resistance is called inertia or lag. So we are getting into the terms used in control theory. These are the realities of physical systems. If you implement your correction now, boom, it requires a time t for the impact to manifest physically. I mean, it's just like you are in a very cold environment and you know that you have hot water in your tank, in your tank, you have a boiler in that environment. And then you switch on the valve for a time t. It is cold water, very cold water that will flow out, right? Because the water in the pipe is cold, and then it is going to take time. It is only the water in the boiler that is hot. So it will take time for the water in the boiler to flow into the pipe. And for it to do that, it needs to flush out the existing cold one in the pipe. All right. So when you turn the knob for the hot water immediately, right, and then you test it, you see that it's still cold. Then you turn the knob again, and you see that it's still cold. Then you turn the knob again. You realize that those effects are being stored. By the time the hot water comes out, it will come out very hot because you have overcorrected for the error in quotes. And that is where we begin to talk about overshoots. So note, we have discussed lag, right? Now we are talking about overshoots. That is overcorrection of the error, right? So let's look at the sequence of events. Overshoots occurs when the controller pushes too hard before the process has had the time to respond. You know, the controller is an electronic device, right? And it operates in milliseconds. The process itself is physical and it obeys the laws of physics. Water will take X time, X seconds rather, to acquire heat. Heat accumulation is gradual. And heat is a very perfect example of, we use a lot in process control, especially when we want to discuss PID. because you can easily demonstrate your lag time, right, and overshoot in a temperature controlled process. Okay, so let's look at this sequence of events. So you have your SP changes, right, or disturbance hits. So two things that you can use that can upset the process. So the process, let's assume that it's in a steady state. If you change your set point, right, it is going to influence the error. Or if you change, if disturbance occurs, it is also going to influence the error. So once any of these changes, either SP or disturbance hits, there's going to be a large error, right? And then the controller immediately, because the controller operates in milliseconds, it will respond with a large MV output, right? E.g., 100% it, supply 100% it to the process. And then the process starts rising, but it will be rising slowly because of the inertia or because of the lag. By the time PV reaches SP, MV is still high, right? And controllers still see some error. So you can begin to see the disparity now. The controller cycle is in milliseconds or even seconds. The physical process cycle is, based on, depending on the size, could be in tens of seconds or even minutes, depending on the size of the process. So because of this, the PV overshoots SP, right? The process has too much momentum. And then the error reverse sign, the error that is positive, now that the PV has exceeded SP, it becomes negative because XP minus PV, right? If PV is greater, then error will become negative. So the controller again acts in the opposite direction. And then you now have PV oscillating around SP, and then gradually the damping effect will occur. So it goes up, goes down, goes up, goes down, goes up, and then it damps and then stabilizes. So you now realize that all the adjustments, the PID adjustments we are doing is, number one, to reduce this oscillation, this up and down oscillation, number one. Then number two, even when there is oscillation, the rate at which the damping goes off, we want to be able to reduce it also. So you can begin to say that PNID is not something really complex in that sense. But when you introduce PNID, when you introduce PID without building intuition like this, it becomes intimidating because all the person will say is differential calculus, integral calculus, and then you begin to ask yourself, how does this affect the physical or the process and controlling, right? So oscillation is energy imbalance. That is that oscillation around the set points, right? It drives. So oscillation is a sustained overshoot pattern when the controller corrects too aggressively. So it drives PV past SP. It overcorrects. It detects the reversal and then corrects back to SP again under correction. And then the cycle repeats itself, often with the same amplitude. So that's why you now have that sinusoidal wave over the SP, just going up and down, up and down. All right. So stability. Over time, right, the error decreases and then the oscillations decay, right? And then PV will settle near SP and then stays there. And then your SP minus PV will be as minimal as possible, right? So formally, a stable system is one where the long run value of PV is close to SP, right? And any transient deviations caused by disturbances or set points eventually die out. So stability is controlled convergence, and it happens over time, right? So if we begin to look at example, when we say there is a grid collapse, essentially what is happening is that the grid strayed away from the 50 hertz frequency because the SP, the set point for our grid is 50 hertz, right? So that is the grid frequency, the actual grid frequency is the PV, which is a process variable, but the set point is 50 hertz. So every time we are looking at the error, once PV strays away from 50 hertz by, I think even by as low as 0.5%, we experience a grid shutdown. I think the percent error, the percent variation is 0.05. So you can either have 50.05 or 49.05. Anything outside that range, you have a collapse. And all of that happens when, all the generators in the country, they're connected to the grid and they're all maintained at 50%. So if there is a very high demand, boom, of power, right? Once there is high demand, it drops the frequency. It drops the frequency rather, and then everything collapses, right? And if there is a sudden disconnection, right, of a high load on the grid, the same thing occurs. So the governor set point is the SP, the target operating speed. The governor is the device that controls the generator, the turbine, whether steam turbine or hydro turbine. So when load suddenly increases, the frequency drops. So you see error. The governor will increase the gate opening, which is a corrective action. If the governor responds too aggressively, the frequency overshoots above 50 hertz before settling. So the same pattern, error, gradual correction, potential overshoots, then eventual stability. So the key terms here is we have the overshoots, we have the settling time, right? That is how long it takes for PV to reach and stay within an acceptable band around SP, right? Typically plus or minus 2% or plus or minus 5%. And again, that depends on the process you are running. Some process requires a very tight variation, minimal variation across the set points. So stability, the property of a control system where deviations from SP decay over time rather than grow, right? So stability, essentially the process that brings the system deviation closer to SP, right? And then oscillation, the repeated swinging of PV above and below SP due to over-aggressive correction relating to process lag. All right, so let's look at the next, so the walkthrough. So this is just, a walkthrough on the simulation we'll do in the next lesson, right? So in this walkthrough, you will run the same timer process with 3 different controller settings. So the controller settings essentially are the values your P, your I, and your D takes, right? So that is essentially what we called the tuning, your controller tuning, right? When you select values for your proportional term, your integral, and your derivative term, right? So as we discussed, you can be conservative. Allow the tuning. Conservative will take a bit of time to settle. You can be balanced. Sorry, you can be conservative and you can be aggressive. And then you can be in between. All right. So these are the 3 simulations we will do now. We click the aggressive preset button. This sets the KP. This is the proportional time to 4.5, key height to 0.2, right? So you get a strong and fast response. So you click start and watch the temperature charts. So what you should see, the temperature rises quickly towards 60 degrees. It overshoots, right, going noticeably past 60 before coming back. And then the error chart spikes, reverses sign, then goes negative when T is greater than SP, then it converges. The system eventually settles, but it took a detour above targets, right? So why? The controller pushes hard, it pushes MV, that is the correction, near 100%, while the 45-second timer lag means the process is still moving after MV starts to reduce. So the result is excess. The result is excess, and that is the classic overshoot. Does this make sense to you?
Yes, sir.
Okay, great. So the same thing in the conservative and the same thing in so we run the conservative, then we apply the disturbance, and then run the balanced, right? So let's just go to the simulation so that we can. So I will explain this screen. So this is the temperature response, right? This is the error signal, the SP minus PV, right? So these are the 2 things we're going to observe. These are the presets. This is the conservative, this is the balanced, and this is the aggressive, right? And these are set by the process engineer or the control systems engineer. And these values are written into the PLC, right? Just to provide that context. So those values are written into the PLC. These are the values you see on your HMI. So the process variable is presently at 30 degrees. The error, which is SP minus PV, is 30 plus 30, right? That is, the process variable is much lower. It's much lower than the set point. And then the heater is not supplying any heat. The time presently is 0 seconds. Cooling disturbance at T equals to 150 seconds. This is the disturbance we programmed into the simulator. So it's going to be introduced at 150 seconds. So I can choose to, maybe because of time, let me use times 2 speed, and then let me start. Right. So you can see the time running. You can see, so you can see that this is approaching set point, right? And you notice the oscillation across in the error here, right? It's going up and down. I'll still repeat this, right? So the run is complete. The maximum overshoot here is plus 2 degrees, which is acceptable, right? Now let's look at aggressive. So this is the aggressive preset, right? And then let's click start. So again, the cooling disturbance is introduced at 150 seconds. So just observe. We'll repeat it a few times so you can see the error was introduced here. So you can see the variation, right? The maximum overshoot here is plus 0.5 degrees, right? Which is acceptable. And then you have your conservative. Oh, sorry. You have a conservative. Let's choose this. So you look at the response. So the disturbance kicked in, and then look at the variation. So you have no overshoots, right? And then it gives you a very clean response, right? And what you have just demonstrated, right, have energy implications. Because when you do, there are a number of considerations that goes in the kind of ways you're going to respond to your um, disturbances, right? When there is overshoot means that now this ether maybe okay, we should have looked at the value at which it reaches set points. That is the value of this MV ether, right? At set point is the maximum energy you need to maintain stability. Any energy you supply that causes it to overshoot is excess. So essentially, you have wasted energy. And energy is a critical cost factor in the plant. All right. Let's run the process again. I'll use speed 1 so that we can observe. Okay, it will be easier to observe. So let's look at, so run the aggressive again, and then we'll start. So just observe, right? So MV is reducing. So it's generated here. So MV is 92, right? So at 92%, we attain 0.0 degrees Celsius. Right, at 92% of MV, right, we attain stability essentially in the process, right, and then we have an overshoot of 0.5 degrees. Now, all those overshoots already costed money because our setting was aggressive. We pushed MV to 100%, right? So those excess have energy implication. And not only energy, by the time we begin to do the analysis, the MV oftentimes is associated, of course, MV is associated with your final control element, which is either the valve or the motor. When you aggressively open and close valves, the valve is a mechanical system, right? Once you aggressively open and close it, you are reducing the lifespan. You are increasing the rate of the maintenance required for that valve. And the same thing applies to motor, right? But if your process requires such aggressive correction, those are decisions you will not need to make as a process engineer or the control systems engineer. All right. Let's look at conservative. So you can see the significant reduction in it, right? That comes with the conservative setting. So you can see that we used less energy. We used less energy to attain set points, right? To get as close as possible to the set point. And again, so you can look at our error here is 2.6 degrees. And the question is that suitable for your process? Right? Can your process accommodate that error? Even though we desire stability, we desire SP error to be zero, right? But it sometimes does not make any difference when you have plus or minus whatever. The example I gave earlier on the grid can still take about 0.05 deviation from SP and still be okay. But anything greater than that, causes problem, right? So then let's look at balanced once again, and then start. So the maximum overshoot here is 2.0, and it's acceptable. So you realize that, so you can see the difference between the various settings. And this is where the strength of the control engineer is, the ability to tune, to tune your process, right, such that you optimize it. This is where optimization comes in the plants. And this is where the control systems engineer saves money for his organization. And this is where you actually demonstrate your value as a competent and valuable control systems engineer. So I'm sure that some of you will ask, you want to try this. You will have access to this in about a week or two, at least a version of this in about a week or two. You'll have access to a version of this in about a week or two, right? You'll be able to create accounts here in about a week or two, and then you can run through this simulation and use different settings. Okay. So let's continue. So let's quickly do this quiz together. Okay. Let's quickly run through this question, 9 questions. So you can either answer or drop your answer in the chat box. Are we recording this session?
Yes, sir.
Okay, thank you very much. I'm looking for the chats. Okay. All right. Okay. So in a closed loop system, what causes the controller to increase its output? A, B, C, or D? B. Okay. Next question. Why does process correction take time rather than happen instantly? A, B, C, or D? B. Okay. Process have inertia. They resist sudden change. Correct. So in the M5 simulation, when you selected the aggressive preset, that is high proportional gain, the temperature overshoots the set points. What caused this? A, B, C, or D? Okay, B. Which of these describes a stable, well-tuned, closed-loop response? C.
C.
Okay. All right. Which of the following are signs of a controller that is tuned too aggressively? Select all that apply. Should I select A?
A.
B?
C.
Should I select B?
Yes, sir.
Okay.
B.
Okay, what about C?
Yes, sir.
What about D?
D.
D.
Okay. So we are selecting all, right?
I think C is not among.
You
So I
said
don't think C is among.
you don't think
C should be among.
Can we take out C?
we should take out C?
Yes, sir.
So which of the following are signs of a controller that is tuned too aggressively? So we should take out C.
Yes, sir.
Yes, sir.
Okay. What about B? Okay, I'll submit it like that. So aggressive tuning causes overshoot, sustained oscillation, and rapid MV hunting. A persistent gap below SP is the opposite problem. Too conservative tuning, P only. So P, proportional gain. If you use proportional gain in your control, you have a sustained offset, right? And then the MV hunting. Do you know what this means? Hunting essentially is oscillation, and we use it for valve control valves. When we hear valve hunting, it's going on up and down, and it could be harmful to the valve, right? So once you have rapid MV, it is the controller that is issuing MV, but it is the valve that is implementing that MV. So you have it's going up and down, opening. Excuse me. It's going up and down, pum, 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 pum. Right. It could be harmful to the valve. Right. After a disturbance hit at T equals to 120 seconds, the balance preset recover to set point within 60 seconds. What does this tell you about the balance between controller gain and process inertia? A, B, C, or D? Yeah. So I'll wait for you. Yeah, I'm waiting. Oh, okay.
D.
Someone already put B. Okay, I have two Bs. Okay. So the balance is appropriate, right? The controller corrects error faster than the process can drift. Is that it? Okay. So when the controller recovers smoothly without oscillation, it means the gain is well matched to the process inertia. The controller corrects error at the right pace, fast enough to prevent large deviation and slow enough to avoid overshoots. A perfectly tuned controller will prevent all disturbances from affecting the process variable. True or false?
False.
Okay. So which one? I have true and false. So it should be
False.
or. The logic is or. A perfectly tuned controller will prevent all disturbances, all from affecting the process variable.
False. The answer is
Okay.
false.
So I have three false here. So no controller can prevent disturbances. So the controller does not prevent disturbances. It reacts to disturbances with the aim of correcting it. Right. So because the disturbances eat the process before the controller can respond, then a good controller detects the error and corrects it quickly, but the initial deviation is unavoidable. So after a disturbance, a temperature controller overshoots the set point by 8 degrees before settling. What does this indicate about the proportional gain? KP is too high.
KP too high.
Okay.
B.
Any other opinion? B.
B.
Okay. So the overshoot occurs when the controller overcorrects, applying too much corrective action, driving PV past SP. IKP produces aggressive correction. When error is large, the output is large. And by the time PV reaches SP, it still has significant momentum. Reducing KP reduces overshoot, but may slow the response. Option D is incorrect. Both KP and KI can cause overshoot. KP causes faster oscillation. KI causes slower wind-up overshoot. Do you understand that last statement? Wind-up overshoot. So, the basic controller is actually the proportional controller. You know, proportional controller is described by the equation y equals to mx plus c. All right, that's the equation of a straight line. For every x, there is a corresponding y, over the range of that graph. Right. So now, in the study, we realize that if you use proportional only, you always have what we call a sustained offset. Right. Okay. So now there's a need to be able to sketch. Okay. I've noted that. I've loved to. Let me see. Okay. I wanted to make a sketch. So there is a sustained offset when you use a P controller alone. Right. Now, when you now introduce the I term, the integral term, right? The integral term now reduces that offset, that sustained offset. So the integral term wind down the overshoot, whether wind up or wind down the overshoot, depending on where it is on the axis, right? It brings it closer to SP. And in doing that, it goes down below the SP, and then the controller realizes again that, okay, there is a deviation. Then it takes it up again, right? And that oscillation, right? That oscillation around the SP is the winding, right, by the integral term. Eventually, there will be a decay of the overshoots, and then it settles at SP. And then the D term simply makes this process faster. The derivative, which is the rate of change, it makes the rate of change, makes it faster so that you attain your set point very fast. Right. So does that make sense to you? So the raw control you get initially is from the proportional controller, and cost-wise, it is the cheapest controller. I mean, it is the cheapest you can implement. All right, it is the cheapest you can implement. K high is more expensive. I'm sorry, P high rather is more expensive, and then PID is the most expensive. As time goes on, you'll begin to because for us, or for me and for many colleagues, it's not just about the technical effect of influencing the process. It is the bottom line that we are concerned with. The plant manager comes to me and said, therefore, my energy consumption is too much. Or I noticed that in the last 3 months, year on year, my energy consumption increased by 10%. What exactly is happening? I've not changed anything. My rate of production is the same. So why am I using more energy? And if energy consumption, maybe 1%, if it causes 100,000 naira, then if your energy consumption increases by 10%, that means that you are incurring 1 million naira in addition to your production cost. And that has reduced the profit margin of the organization. So you call in the control engineer, and then the control engineer now begins to investigate. Right. The first thing it does is it looks at your tuning. So it tries to do tuning. And then what are the causes of those deviation? Maybe you missed some maintenance activities on your valves, right? Maybe there was a process upset and there were a lot of valve haunting. Pam, 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 I mean, going up and down, going up and down. And then there are some wear and tears in the, we call it the valve trim. The valve trim. We'll discuss the features of a valve in the paid whatever we're starting next week, right? So there are wear and tear in the valve trim, and it has left some allowances, and then the lag time of your process has changed. Maybe it has increased, and then the tuning you did last quarter or last year does not apply anymore to the condition of the process now, right? So you now come in as a control system engineer, you look at all of this, your equipment, or probably they even change some transmitter along the line, and the transmitter they change is not like for like, right? So all of these things, you come in and then you tune the process again, putting into consideration the condition of your control valve, the condition of your pipelines. Maybe you have some material buildup within the pipeline. There is pressure increase year on year, and so on and so forth. So you come in, you tune it, you adjust your KP, KI, and your KD, right? And then they measure for another 2-3 months, and then they discover that there is a reduction in energy consumption. And that translates that the control engineer has given money to the plant and has increased the plant bottom line. All right, let's finalize this. So the tuning presets are available: conservative, no overshoot, slow settling time, aggressive, fast response, oscillate briefly. For a safety critical steam pressure controller, which would you choose? So this is an application question.
B.
Huh? B? Okay. So you can say that it is safety critical. So when I say that the setting you use depends on your process, right? So conservative is preferred for safety critical, steam high pressure systems, reactive chemicals, right? For such critical processes, it's better you are conservative, because oscillating pressure can trigger false alarms. It can stress mechanical components, and it can potentially breach safety limits. And of course, we will not depend on you, on your initiative in the plant to do conservative setting when it comes to safety critical systems. We will have implemented interlocks. Maximum values you can even set. You cannot even get to the point where it will be dangerous. Right, so we'll have implemented all of those in the program. All right. But just for the sake of this exercise, for you to understand, that's why we are having this. The interlock of the process, the permissive, will not allow you to do anything aside conservative in the real plans. Do you understand? Exactly.
Yes, sir.
Okay. All right. So I guess we're done here. So we'll finish the quiz and nice. 100%, 40x per hand. And then that's a summary, right? So let's go to process dynamics and constants. These are the theories behind the process. And again, I'm emphasizing that understanding this is very, very important, right? Understanding how to program a PLC is good, but these are the things you actually code or program into the PLC. So for example, now you can write a functional PLC program, a ladder logic program, right? Let me ask you, what is the importance of your scan time in PLC programming? Who can explain that? Your PLC scan time. What is the importance? You said?
The scan time is the time it takes to read input, execute the program logic, update the outputs, and then run diagnostics and start again.
Correct.
So its importance is it tells how fast it does that in a second. Some PLCs do that in milliseconds, and some controllers do that in seconds.
Okay. Yeah. So now that's a very good explanation. Thank you for that. So how critical is this? So do I need to calculate my scan time when I'm designing my program? Do I need to put that into consideration? How critical is it to the program I'm writing? How concerned should I be? Anyone? The explanation you gave about the scan time is perfectly spot on. The time it takes to read the input, execute the program, update the output, run diagnostics, and then start again. So it's a time T, right, in seconds. So how critical, what is the importance of that scan time when I'm writing my program? I'm not going to tell you. I'm going to give you as an assignment. If you don't tell me.
It influences the response time of the process.
You said?
It influences the response time of the process.
So, okay, what should be a typical scan time for a process? 1 millisecond, 5 milliseconds, 10 milliseconds, 1 second, 2 seconds, 3 seconds.
I think scan time depends on many variables. For the few times I've monitored scan time, I think some of them are 150 milliseconds, and I believe some PLC should be faster than that. But the question you asked, the importance, I think this is the first time I have actually heard that question, and from the way I see it, I think it is important to consider scan time when creating your program because it tells you how fast the system can detect a change and respond to that change.
Also, okay, so that is one. Yes, it tells you how fast a system will change or respond to that change, right? And that is, yeah, that's an answer. But there is another answer that when you are writing your program, so because if, for example, you write a program, you write a PLC program that is, let's say, 100 rungs, and you write another one to do the same thing for 50 rungs, that is, you use half of the code, you optimize your code, right? One will execute much longer, let's say 10 milliseconds. Another will execute much lower, 5 milliseconds. The implication is this. If you have, you know that once your PLC gets into a scan, once it starts reading the input, right? Let's assume that it reads a pressure transmitter or a pressure switch. That is the first thing on the rung, right? It reads that, pump, and then there are 10 other sensors it needs to read before running the program. The first one it reads, if that first one changes within that scan time, it is going to ignore that change. Do you know?
You're right, sir.
Now, if it ignores that change, and let's now assume that that transmitter is tied to a very critical parameter, it is monitoring a critical parameter in the plant, or let's say, for the sake of this discussion, a safety critical parameter. That is between the time the PLC started reading and the time it completes that particular scan, the condition of the process has changed. You know that that can constitute a very dangerous condition in the plant. Do you agree?
Yes, sir.
So, which means that when you're writing your program, you need to have an understanding of the type of process you are running, the rate of change, the lag time, the first order behaviors, the inertia. You need to have all of those in your understanding and factor it in your program. That is where we begin to consider the scan time of the PLC. Right? The analogy is this. Someone put a fried meat in front of me and said, Apple, watch it all. Don't take your eyes off it. Right? And then I love tennis. So I just hear on the TV that Sinner just hit a winning shot. And then I just took my face off to scan that TV momentarily. By the time I turn back, the cat has taken that meat. So the incident already occurred. So your scan time needs to be planned and well designed, right? Such that even if the PLC takes eye off that critical transmitter, we will have checked that there won't be any problem within the scan time. That even if the state of that transmitter changes after it has been read, right, it will not constitute danger to the process within the scan time. Does this make sense to you?
Yes, sir.
So this is where we separate the men from the boys. You can drop XIOs, XIC, and all of those on a ladder rung, right? I mean, and then we'll say, oh, it's working. My program is running. But then optimization, comes in. And you cannot optimize if you don't have understanding of all these things you are talking about. So that's why I said that foundation is very, very key. All these theoretical foundations, these are the things that you now impute into your program. What you will implement with a line, an experienced programmer will come and say that, no, I'm not going to use one line. I will implement this with 10 lines, simply because that experienced programmer is checking, is building safety and efficiency into that program. So, for example, that first sensor in that scan, you scanned it, right? And then you take the PLC ignores it until the next scan time. An experienced programmer, if he sees that the process lag or the PLC scan time is too much, will constitute a rig, then that programmer will read that sensor maybe about 2 or 3 times within the scan time. It will dedicate other rungs or add conditions, to check the state of that transmitter maybe a few times during the scan time, so that the process will not be exposed to dangerous conditions while the PLC is running its scan. I hope this makes sense to you.
Yes, sir.
Yes, sir.
Okay, fantastic. So let's continue. I had to. Okay, time is gone, but we can still quickly run through this, right? Like I said, I mean, this particular one is a free course. It will be on the platform. So in about 1 week, maximum 2 weeks, you will have access to this. So you can revise this at your own leisure. All right. So every control, why process don't respond instantly? Every control engineer eventually asks, why can't I just set the output and have the process get there immediately? The answer is in the physics of every industrial system. And understanding it changes how you approach tuning forever. So we have inertia, right? All physical systems resist change. And this is not a design flaw. It is thermodynamics, it is mechanics, and it is fluid dynamics at work. These are physical properties of materials that we need to live with, we need to design around, we need to consider. Right? So, system, what resists change and why? This table is not rendered rightly. Apologies for that. But so you have heated tank, right? The thermal mass, and then energy must flow in and out of mass, right? You have liquid level, vessel volume, then flow rate limits how fast the level changes, right? So how fast does the level change will determine on the size of valve you're using, the percent opening of that valve, right? So if you have a motor shaft, you have rotational inertia, right? That is what resists change here. So torque must overcome angular momentum. You have gas pressure, you have the factor called compressibility. Gas must flow in and out of volume. All right. So when you open a valve 20%, the downstream pressure doesn't jump up instantly to a new value. When you increase heater power, the temperature doesn't immediately rise to the new equilibrium. Energy and mass transfer take time. I mean, this is just basic physics, O-level physics. This time dependency is what we call process dynamics. When you begin to talk control systems in terms of process dynamics, you're going to get a lot of respect from people that knows. And that is when you begin to transition from being a technician into an engineer. The engineer designs systems using the principles of science. The engineer designs systems by applying the principles of science. Science seeks to understand the natural behavior of systems. So once science have that understanding, the engineer now takes that understanding and then design or engineer a system around the given nature, because the natural state is a given. There's nothing you can do about it. Then we now design a system around it. You write your program around it, your ladder logic, you consider the lag time, you consider the speed, you consider all of those things. And that is where you differentiate between the technician and the engineer. The technician knows how it works. The engineer knows why it works. And every realistic process model must account for it. Right? So that's why we don't bother the technicians with calculations, with modeling. It is the engineer with stress and we say, you need to understand the modeling. You need to understand the calculations behind it. For example, we're not going to bother the technician on the KI, KP, KD. We'll just tell the technician, if you see this problem, just turn this knob a little. This is what you will see. It is just a physical observation. It is the engineer that goes inside the process in his mind and begin to look at the interactions, begin to evaluate the physics behind it. Create a mental model of the plant. Essentially, you create a digital twin of the plant in your mind as you begin to troubleshoot, write your programs, or optimize. All right, let's move a bit faster. So first order, most industrial processes can be approximated as first order systems. Right, now we're going into modeling. Right. For the people doing CAP, I regularly teach them process models. I think I'll be taking one maybe later this month or early next month. I even need to check that date. Right. So for the CAP exam, process model is a topic that it's a hurdle you need to cross. So most industrial process can be approximated as first model systems. After a step change, the output follows an exponential curve towards its steady state. The exponential response pattern. So start fast. There is a large gap between current value and target drives rapid initial change. Then slows progressively. As the gap closes, the driving force diminishes. And then it never quite arrives mathematically, but reaches 95% of the final value in approximately 3T and 99% in 5T. This is just a description of the exponential function. Right? So if you don't get this 100%, don't worry. Just have the idea, right? This is a fundamental course, right? Essentially, it is to show you it is there and it exists, right? When you need to go deeper, to wade a bit deeper into the water, at least you will have taken out the introduction. So it's the introduction you are doing, right? So this is why industrial trends looks more often like a smooth S-curve flattening out rather than a sharp jump, you are watching first order dynamics in real time. Right? So you actually never, for first order behavior, you never arrive at set point. There is that slight deviation. That slight deviation is significant improvement over the proportional term. Right? So that is what the first order behavior is. And then you have the time constant, a speed label for processes. So the time constant is a single number that characterizes how fast a process responds. Its definition, after a step input change, tau is the time it takes the output to reach approximately 63.2% of its final value. Right? Why 63.2%? It comes from the math t at tau, an exponential process reaches 1 minus e raised to power minus 1, approximately 0.632. I was on a project last year, around September, October, for an oil company. And when we were about to do the commissioning, I had to defend certain decisions we made. And one of the things I had to defend was the time constant. That is, the process time constant must be less than 5 seconds. And I had to write a lot of mathematics and whatever. I think I'll make it, we'll be introducing some case studies, right? After we finish these fundamentals, we have a few more courses to finish these fundamentals. We will introduce some case studies so that you can see all these concepts, how applicable it is in the plants. And it's a very important, and I mean, these are the things that distinguishes you, because it might not be obvious to you, but people that know it knows it, and it is regularly being applied in processes. Right? I had to write, I think, about 5 pages justification on process constants, right? Because it's a safety critical system, right? And then, in fact, the specification for the project says that the standard says that the time constant must be less than 5 seconds. So I had to justify and prove the value we got. All right. So that is how I mentioned that, so as to know that we're not just talking mathematics here. We're talking application. Right. We're talking application. Right. So why 63.2%? It comes from the maths at t equals to tau, an exponential process reaches 1 minus e raised to power minus 1, which is approximately 0.632. Right. I'll run through this, and then in our next lesson, we'll come back again to this too. Well, that's if it still interests you. Because I'm not seeing any reaction. Looks like I'm taking you to where you don't want to go. So,
Yes, sir, we want to just stay in wrap.
You said?
I said we really want to go there, but we are just being very attentive, paying wrap attention to it, so that we don't miss anything you are saying. That's why, sir.
Okay, cool. So I mean, again, I'll give you access to this in about a week or two, and then we probably might be able to do this tutorial every Saturday morning like this, because it was 2 weeks initially because of the stress of creating slides, right? But as I add more lessons to this platform, then we'll just open it, and so we'll have more interaction and be able to move more quickly. Right. But the case studies will come in, and then some other concepts to make learning more sticky. So a small t equals to fast processes, or process rather. Large T equals to slow process. This is the most important intuition in process dynamics. And as a side, I'm going to encourage you guys, some of these things you are learning, right? Even if it is this time constant, number one, I expect all of you on the call to have a functional LinkedIn account, right? Because LinkedIn is now the official CV of everybody. If I want to hire you, one of the first places I will go to research you is on LinkedIn. And you want to be sure that when I go there, I have solid evidences of your capabilities, at least to get you an interview. And then during the interview, you can now prove what you know or what you don't know. And when people say, "Oh, I don't know what to post," I mean, if this time constant is a new thing to you, then just write 5 or 6 sentences on time constant. Process time constant. You don't have to claim that you have applied it, but you can express your understanding of process time constant. And anybody that sees this will say that, okay, this person is going beyond the peripheral of control systems. You are actually doing process control. The instrument engineers deals with instruments, that's all. The control engineer, the control systems engineer deals with the control systems, but must understand the process is controlling. So begin to drop, even if it is 2 lines, 3 lines, or read a bit more about it and the significance, and put it on your LinkedIn. Create that CV continuously, and because LinkedIn is an online platform, once you put it there today, it is time stamped that you put it there today. In 3 years' time, if I'm researching you and I see that as of 3 years ago, this person has been dealing or studying or talking about time constants, I can only imagine the level this person will be by now. So that's just a tip for you. So why it matters? The time constant tells you how aggressively you can tune the controller. Fast processes, that is small tau equals to 15 seconds. The PV changes quickly in response to MV changes. A controller that was perfect for a slow process will overreact, causing oscillation. The gain must be reduced to match the process speed. So you can begin to see the application now. That you cannot say that, oh, in this plant where they are manufacturing soap, they use this set of parameters to tune their process. And you now carry that same value. You take it to another factory where they are manufacturing soap. And then you tune it like that. I mean, you're going to cause problem because the process constant, the time constant varies, right? So for slow processes with large time constants, this should be approximately 80 seconds. The PV responds sluggishly. A controller tuned for fast process will appear unresponsive, taking minutes to correct errors. Larger integral action is needed to accumulate error over the long settling time. Mismatch is the root cause of most tuning problems. Are you following? So
Yes, sir.
before tuning any controller, experienced engineers run a step test. A step test, when we say step, a unit test, I mean, you inject an impulse and then you measure the response time. All right. So you put the loop in manual mode, you apply a step change, e.g., you jump from 40 to 60%. You record how the process variable changes over time. You read off time constants. You find the time when PV reaches 63% of its total change. You also read dead time, theta, the flat period before PV starts moving. This step test gives you the process parameters you need to calculate controller gains rationally rather than guessing. You know, I speak to some people and they'll say, oh, if you want to tune a controller, you use Ziegler-Nichols, you use this, you use this. Yeah, I mean, it's good that we know the term. But these are the inputs into even those formulas. Even a valid method is also trial by error. Even the trial by error will be more efficient if you understand the relationship between the time constant, the dead time, the lag, and all of those process dynamics. Right. So, real world, in a hydropower station, the process is mechanical. Turbine speed has a time constant driven by motor inertia, typically 4 to 8 seconds. Gate position is hydraulic with servo dynamics, 0.5 to 2 seconds. Penstock pressure response in milliseconds. A governor must be tuned knowing these different values. The speed loop needs different gains than the pressure loop, right? The speed loop has a fast time constant. The pressure loop has a slower time constant. Using the same controller settings for both will cause instability in one and sluggishness in others. Of course, you know that this example has to do with the heat we are facing in the country presently. Right, the weather is naturally hot, but our control system is not well tuned to counteract the effect of the weather. Essentially, what I'm trying to say is that we don't have power. That is the bottom line of all the Oyinbos have been saying. There's no power. Why don't we have power? Our generation station, I mean, so many reasons actually. Don't let me stretch it. But a governor is a controller that controls the movement of a turbine, whether the hydro turbine or the steam turbine. All right. So in the governor system, you have the speed loop, you have the pressure loop, right? And both of them have different time constants. Your controller settings for both must take account of their time constants. Right. So the key terms here, we have the time constant, we have the first order response, which is an exponential approach to steady state value characterized by a single time constant. Right. The step test, the process gain, and then the dead time. You can just take a picture of this and master this. This will form a good LinkedIn article. All right, just take a picture of that and be diligent and write about this and let it be there on your LinkedIn as you continue the study. Right. Can I proceed?
For me,
Can
yes,
I
sir.
proceed? Okay. All right. So, not sure we'll finish this, but let's agree to finish by 8. Sorry, by 9. The 9 o'clock your time. All right. So, this is the exploration, measuring and using the time constant. This walkthrough takes you through the 2 experiments that define M6. That's module 6, measuring time constants from a step test and observing how the time constant affects controller behavior. Follow each step before clicking continue. And you'll begin to see this is the value of this simulator, right? The simulator is not designed just to give you that, what's it called now? To give you that adrenaline jump, or I program the PLC and I see it's working or whatever. It takes you into the fundamentals, the behind the scenes, helps you to demonstrate that. So you click apply step or start if the step is auto applied, and watch the response. The process output Y starts at 0 and begins rising towards 1.0. A dashed horizontal line marks the 63% level. That is Y equals to 0.63. The simulation measures and display the time constant, which is approximately 45 seconds. Recall that the time constant is the time it takes the process to reach approximately 63% when you apply a step change. All right. So you observe the response is smooth. It accelerates at first, then slows as it approaches 1.0. This is the exponential first order shape. The time constant display should closely match the selected days. This is what engineers do before tuning. Run open loop, measure time to 63%, and use that to calculate rational controller gains. Is school still a scam?
No, sir. Our school is not a scam.
The mathematics you learned at school, is it making sense where the application is now?
Very much, sir.
Yes.
Making sense.
I tell people that for me, my experience in engineering, I have actively used differential calculus on the job. I mean, yeah, our experiences varies, but I think I have been a bit fortunate in the kind of opportunities I've been exposed to, So step 2, you compare fast versus slow process. Without changing the controller, switch tau to fast 15 seconds and then run the step test. Then switch to slow 80 seconds and run again. Compare the 3 curves. What you should see out of this, we'll see that the process physics are identical, just the time scale changes. The key insight is the controller output causes the same final service state, but the speed of arrival is entirely determined by the time constant. This is why you cannot use the same controller gains for a fast process and a slow process. Right, and that's an insight. So we're now talking about a fast process and a slow process and the types of gain you use for both. And then the step 3, you switch to closed loop control. You set mode to closed loop and try each time constant setting with the PID controller active. What to observe with T equals to 15. The controller can act quickly because the process responds quickly. With default gains, response is fast with small overshoot. But if you increase KP too much, oscillations appear quickly. Fast processes are less tolerant of aggressive tuning. And what to observe? Even with controller active, settling takes a long time. Integral action is crucial. Without it, steady state error will persist. The same KP that caused oscillation on process time constant 15 looks perfectly smooth on time constant 80. The mental model. Slower processes are more forgiving of high gain. Faster processes punish aggressive tuning quickly. Matching controller speed to process speed is a core skill of loop tuning. And then reflection. You consider what you've observed. Step test first, tune second. This is the professional approach. Before touching KP or KI, understand what process, what the time constant, the time constant the process has. It tells you how often the controller needs to act, how large the gains can be without oscillation, whether derivative action is worth adding. An operator who knows their process time constants can estimate a reasonable starting point for tuning without running through hundreds of trial and error combinations. That engineering knowledge is what separates systematic tuning from guessing. In the simulation L3, you freely explore the time constant with both modes, measure these from steps, and then tune the controller across different process speeds. Then the quiz L4 will test your understanding of how the controller, how tau affects the controller design. All right. Should we continue or 53? Okay. Anyway, if you want to drop off, I mean, this will be recorded or this is being recorded and it will be shared. So these are the activities, right? Set mode to open loop step. So this is the mode. So this open loop, this is closed loop, right? So you set your mode to open loop test, right? And T to medium. So this is the time constant. This is slow. This is medium. And this is fast, right? So let's select medium. This is our process output. This is error. And this is the measured T, right? So run and watch where the output crosses the 63% line, right? So you watch where this output, so this is green is a process output, this is a set point, and this is the 63% mark, right? So let's apply step. So did you notice that? Did you notice when it crossed that 63% mark? Let me reset. I suggest you if you can take your phone and record so that you can have a look at it later. All right. Take your phone and record the screen so that you can have a look at it. Later. the recording will be shared, will be sent out maybe on Monday or Tuesday. So you might want to quickly have a look so that you can, cement that understanding before the recording is out. Right. So let's apply so we'll still deal with medium and then apply this. Okay. So you can see the expected is at 46. Oh, sorry. Sorry. Oh, apologies, guys. Right. Reset. Let's move a bit faster. Right. So let's look at the slope. Let's look at the slope. Apply. So slow is at time constant, 80 seconds. Right. So the measured time constant here is 79.5. Right. So you can see the difference between the two, right? So let's run at 15 seconds. You can see how fast it is moving. Right. And then we can switch to the closed loop, right? And then let's just run at this. So you can see. So there's lots of I need to, okay, my own time is up now, right? So okay, oops. So let's quickly let's look at this. So mismatch slow. Okay. A controller is tuned for a slow process at this. It is then applied to a fast process, t equals to 15. What happens? Nothing changes. The controller. Sorry, I'm in a hurry now. I need to attend to something. So nothing changes. The controller adapts automatically to any process. The controller is too slow for the fast process. High steady state error. The controller is too aggressive. The fast process causes oscillation and overshoot. The controller speeds up to match the controller setting, right? So the correct answer is A. A controller tuned for 80 seconds has gains appropriate for a slow process, right? On T15, those gains are too low. So the loop is sluggish and slow to correct errors. So when we look at the time constant, is an important thing to understand, especially the kind of processes we run. And there are different process categories that we can say that this process is a fast process or a slow process. and we know what a fast process and a slow process is, right? So, so like I said, this is an introductory, what's it called now? This is a fundamental course. So if you don't get it 100%, it's fine, right? You will have the opportunity to play with this simulator in a week or two, and then we'll run it over and over. So I want to stop here. I need to move on to something now, right? I want to stop here. We'll leave this, or probably if I'll just run through this question, right? How do I have the time? Sorry. We'll need to leave here, right? And then we'll come back to it. We'll still run through this. I think we'll have our today. So we'll run through all of this before we move on to, so that's M6. We're on M6 now, before we now move on to M7, right? So I think we can conclude this next week, and then we can conclude M6 and M7 on Saturday. All right, and then we move to alarms and safety basics, applied control, case study, and then capstone. Right. And one of the strengths of this simulator again is that with the PLC simulator, you can simulate the effect of the process time constants, right, on the PLC, and you can see. So that's why we measure the scan. That's why we measure the scan here. So you can do that scientific measurement, right? Factor in the time constants, measure it, and see the effect. And it helps you to be a better PLC programmer. Yeah. Okay. So, thank you very much. Any question? Let me quickly take questions for 2 minutes before running along. Any question? Nobody's talking. Now don't vex. Hello, am I still online? Okay, can anyone hear me? Oh, okay, great.
Yes, sir. Yes, sir.
Okay. Oh, no question, right?
Yes, sir. From here.
Okay. 100% understanding or 100% confusion.
I think just some of us will still have to like go through the recording. Yes, sir. But for that, I think it's
Yeah.
a question. Yes.
Yeah, I mean it's and it's a good thing. You understand that you are learning when you have questions and you have conflicts, right? It is when you now go back to it again the second time, the third time, and once the concepts stick, it sticks forever. But believe me, to program. I mean, I'm not talking about even if you're writing a program for a drive or for a motor, for certain critical processes, you need to consider all these time constants. I mean, if you're writing a program for a motor that is used for grinding animal feed, for example, I mean, you have a lot of margin for errors, right? But if you're using a motor that is mixing pharmaceutical components, then we now begin to talk about precision, right? You need to be able to say that this program will scan within X time and it is going to implement this, and it's not going to ignore a particular reading if the state of the process changes. Right? So But that's fine. It's a good thing we're learning together. Even for me too, a number of things are being refreshed as I'm talking about it. So I will say again, thank you for sitting and listening to me. All right. On this note, I think we can safely shut down the class and we will continue next week, Saturday. Have a fabulous weekend.
Thank you, sir.
Remove that basket, come now. That's it.
Thank you, sir.
Thank you, guys.
Thank you, sir.